Good morning and welcome to the third and final session. So in the first session we saw seminaries, fitting, interpolation, extrapolation and numerical differentiation and integration. The last session we spent lots of time looking at some linear algebra concepts like eigenvalues, eigenvectors and performing coordinate transformations. What is the physical meaning of these eigenvectors, eigenvalues and things like that. Today we are going to continue with the linear algebra portion. We are going to talk about one last topic, which is solving simultaneous linear equations. As we saw in the last session, sometimes after getting the eigenvalues, you have to get the eigenvectors, and getting eigenvectors basically boils down to solving a set of linear equations. And there are also other contexts you will see that such solving simultaneous linear equations becomes very important. After we do that, we will do some optimization problems. So there are two things that we will take up. One is optimization of a polynomial in a single variable. I will not do the more complicated ones. It's sort of unconstrained. There is a range of values that is allowed, but within that it is unconstrained optimization. And then we will do a simplex method to solve a linear programming problem. And then finally we will try to solve a couple of ordinary differential equations. So that will bring us to the end of these sessions, and these are primarily the numerical techniques that one needs to know. So like I indicated last time, many problems of practical interest, we need to solve a set of linear equations simultaneously. Okay, so there are n number of unknowns and there are n equations and you are trying to solve them. The eigenvector computation is an example. So we will discuss some numerical methods to solve systems of simultaneous linear equations. Okay. Again, these problems are chosen because they are amenable to hand computation. So let's look at temperature dependence of linear thermal expansion, for example. Right. So this is in boron nitride in the temperature regime 77 to 1205 Kelvin. The temperature versus linear thermal expansion is listed, and the linear thermal expansion is given with the standard deviation. Okay, so with the error. What we want to do is to fit this data, and fitting this data means that okay, so it is known that this temperature dependence has a quadratic dependence on temperature. That is, alpha is some A naught plus A1 temperature plus A2 temperature squared, where temperature is in absolute scale, okay, in Kelvin scale. So the problem is to identify the constants A0, A1, A2 using the least square fit. See, we have already discussed the least square fit. We have seen how to do it if it is a linear fit. Now, if it is a quadratic fit, how should it be done? So least square fit ended up with two equations, right? One mx plus c. So m and c have to be identified. So we ended up with two equations, which by solving we got the solution. Now same technique can be used. So you take the data yi and you subtract a0 minus a1 xi minus a2 xi squared whole squared. So which is basically the square of the deviation of the experimental points from the fit that you are trying to achieve. You sum them all up, so it becomes least square fitting. It's quadratic, no longer linear, because the polynomial you are using is quadratic. So now you have three equations that you can generate by trying to minimize this quantity. Okay, so this quantity differentiated with respect to a0 should be equal to 0, differentiated with respect to a1 should be equal to 0, and differentiated with respect to a2 should be equal to 0. So you end up with three equations, and those three equations, when you try to minimize with respect to a0, a1 and a2 the summation value, then you end up with something like this. So there is some method you might have noticed in the linear method itself. So it is the number of data points, summation xi squared, summation yi. Now this on the other hand is summation xi squared, summation xi cube and summation xi yi. And the third one is summation xi squared, summation xi cube, summation xi power 4 and xi squared yi. So basically I mean one summation, one power keeps increasing in the summations every time. Okay, so this is the set of equations that one wants to solve. So you can see simultaneous linear equations are important, for example, in nonlinear curve fitting. Okay. So, and the next one, in matrix form, this can be represented. In the matrix form, we represent it like this, right? So it is n and summation xi squared, summation xi squared, summation xi cube, summation xi squared, summation xi cube, summation xi power 4, etc. So if you multiply this matrix with a0, a1, a3, a2, I don't know why it's a3. So a0, a1, a2, then you get the right hand side, which is summation yi, summation xi yi, summation x squared yi. Okay. So I have done this calculation, so it's a little bit crazy because you have x, which is going from 77 to 1205. So x squared, x cube, and by the time you reach x power 4, you are already having numbers like 10 power 12. So this is why it's far more easier if this are done using computers. You don't have to hand calculate. But in any case, so this can be done. It's not difficult. So some of you can check later when you get time that these calculations are right. So you get some summation of this summation x squared, summation x cube, summation x power 4. And of course, you can also do the summation y, summation xy, summation x squared y. Okay, so we have all these numbers, and then you can put them back in the equation. So this is the form of the equation. So this we will use as the basic equation for doing all the other computations that follow. So by solving this set of linear equations, of course, we can find the a0, a1, a2. And so it can be solved. Of course, you can write down the equations. Okay. So first, for example, you can eliminate a0, right? So you basically have three equations. So you eliminate a0 using one of the equations from the other two. So then you get two equations, and those are equations in a1 and a2. And so these two equations which are in a1 and a2, right? So that those two can be solved. So you can eliminate a1, for example, these two, so you will get a2, and if you do that, you get a2 as some 0.0029, and once you have gotten a2, you can substitute here and you can get a1, and you can take a1, a2 values and substitute in any one of the equations, and you can get the solution. So if you do all that, the polynomial that fits the given data is given like this. Alpha is minus 4112.41 plus 8.5059 into 10 power minus 2 times temperature plus 2.9119 into 10 power minus 3 times temperature squared. So by solving a set of simultaneous linear equations, it is possible to do fitting which is other than linear fitting. So this can be done for any order polynomial, for example. It's not necessary it is only second order or quadratic. You can go on to any number of order of polynomials, and the number of equations will correspondingly increase, and you will have a matrix of a bigger size. If it is an nth order fit, it will be n by n matrix and n unknowns which you need to solve for. Then this kind of hand solution becomes much more harder. So you want to have algorithms which will produce the solutions for you. Okay, Gaussian elimination is a method which basically puts it in the matrix form of whatever we have done earlier. Okay, so we have used the elimination method. First we eliminated a0, then got two equations which had only a1 and a2. We eliminated a1 from those two and got a2 as something, and then had the back substitution. So using a2 we got a1, using a1 and a2 we got a0, and so on and so forth. Okay, so it can be made more algorithmic. In that we make what is known as the augmented matrix. Okay, so basically it contains the left hand side matrix, and the right hand side numbers are put as the last column in this so-called augmented matrix. Okay, so for n by n, it becomes there is one extra column. Okay, so it becomes a rectangular matrix, no longer a square matrix. So the first step is to basically reduce this augmented matrix to upper triangular form. Okay, so and for doing that, the allowed operations are interchange any rows. Okay, they can be changed, and any row can be replaced by the linear combination of itself and any other other rows that are available. Okay, so these operations on the augmented matrix to obtain the upper triangular matrix basically do not change the solution. A0, A1, A2 are not changed, and because we are only changing rows and not the columns, the order of A0, A1, A2 also remains the same. So that is very important. If you change the columns, which is allowed, you can do in some situations, but if you do, you have to keep track because your A0, A1, A2 order also keeps changing when you change them. Okay, so that's very important. But if you don't do that, only if you do only row exchanges and replace any row by linear combination of itself with any of the other rows, then the solution doesn't change. The order of the variables in the solution doesn't change. So you can do that. And so you consider the first row, for example. Okay, so in the first row I have a value of 6 here. So if I divide by 6, all the A11 term will become 1 and the other terms will just be divided by 6. Similarly, I can divide this by 3, 4, 1, 6, 4, 6, 8, right? So that is like 34,16,468. So if I divide by this, so this will become 1 and this will become some non-zero but small number. So this will be some other number, some other number. Now, because this can be replaced by any linear combination, okay, I can also make sure that this remains 1 and the rest of it is 0. So I can, for example, divide the value, whatever number that comes here. So I can make it 1 by dividing by that number itself. So then if you subtract this from here, then you will get numbers which become 0 here. And then whatever diagonal term comes at A22 position, then you can make it 1 by dividing it if on all the terms. Okay, so you can initially replace it by making sure that this term is 0, because if you divide this by 6, this becomes 1. So if you divide this by 3810, all of them, then and subtract it and put it here, then because this is 1 and divided by 3810, this becomes 1, so this becomes 0. So this is 3416468 divided by 3810, and that is 3810 minus this quantity divided by 3810, so and so on and so forth. So you can get them, and whatever that number is, now you can divide by that and make this 1, and so the other terms also get modified. And when you come to this, now you have this 0 and this as 1, and so you can try to make these also to be zeros, and only this will have a non-zero value, and later we will normalize it to become 1. So this is possible. Basically this is what we did when we eliminated A0 and then A1 and then got A2 by back substitution, and that is the same operation. Okay, so you can replace the second row using a linear combination of first row minus second row divided by 3810, and that leads to 0 in the 2, 1 position and so on. So this is continued till 1, 1, 2, 2, 3, 3 become unity and 2, 1, 3, 1, 3, 2 become 0. So then the back substitution, because A2 will be directly given by the right hand side number, and using that A2 then you can calculate A1, because A1 plus something A2 will be equal to right hand side, and you know A2, so you can calculate A1 and so on and so forth. So this method is known as Gaussian elimination. But obviously this procedure fails if, for example, on any one of the diagonal terms, if I had 0, I can't divide by 0. So then this procedure fails because that is no longer 1. Okay. So to avoid this division by 0, we use partial pivoting. Okay. So in pivoting, in each column, we interchange rows in such a way that the largest number appears in ith position. Okay, so I think this is already, for example, so this row, if you take this column, you take this is the largest number, and it is at this position. Okay, so and if you take this column, then you would expect this to be here, because that is the largest number and that will be the A22 position, and if you take this you would expect this to be here. Okay, so this kind of exchange of rows to get the largest number at the diagonal position is known as partial pivoting, and if the ith term is not 0, then so we interchange, and even if for example ith term is not 0, okay, even then pivot is useful because the Gaussian elimination algorithm becomes unstable. Okay, round of errors can accumulate and lead to loss of accuracy. To avoid this problem, it is always better to have the largest number appear in the ith position, because if you have it, then you will not have this kind of numerical inaccuracies creeping in. Okay, so because smaller pivot values when they are used in division can lead to loss of significance. So that is the reason why partial pivoting is preferred even if AI is not 0. You know, we have a matrix in which AIs are not 0, but it is still better to do it because it will lead to much better accuracy of solution. Okay, so here is how we do with solution with partial pivoting. You can see that I have interchanged the first row with the last row. Okay, so 63810 has come down and this number has gone there. Okay, so now you divide by 341, 6468, all of them. So this becomes 1, and replace second row by dividing by 3810 all the numbers and subtracting from that. So this becomes 0. And similarly, third row is first row minus third row divided by 6. So third row divided by 6 will make it 1 here, because it's already 1 here. 1 minus 1 will be 0. So this kind of linear combinations we can replace in the augmented matrix. That's what we saw. That doesn't change the solution. So you do that. After you have done that, now you can go to the next step. Okay, so we exchange the second and third rows. Why do we do that? That is again a partial pivoting decision. Okay, so we have attained. So first we wanted to get rid of the first row, first column we want to make 1, and the remaining values we wanted to become 0. So we did the first pivoting because that was the largest number that you could get in that column. Now that we have achieved it, we now look at this next two columns. 365 is the larger number, so I will exchange. Okay, the row exchange interchange happens, and then when I get to this 365 here, I'll divide that by 365.80 all the numbers. So that becomes 1, and now I can put this last row as the second row minus this row divided by 104.09. So that will lead to a 0 here and some other numbers here. Okay, so I have done that. So you have gotten solution like this. Now you can see that in matrix form, if you write the solution, this is rather straightforward. 185.63 A2 is this, so you can calculate A2. And when you have A2, you can multiply 1327.2 into A2, and you subtract it from this, you get A1. And when you have A1 and A2, you can put those values here and take them here and subtract, and you will get A0. Okay, so and you can see that when we did the direct elimination, the numbers that we got are slightly different from what we. So here we have 412.41 for example, but after elimination you get 411.07. Okay, so you can see that the procedure is the same, the operations are basically the same, but numerical methods have this kind of problems. Okay, so they give you with some accuracy. Okay, and that is because there are, by the way the algorithm is implemented, corrections, errors that accumulate. Okay, so corrections have to be done for that. Now you can iteratively improve this solution. Okay, and this is also an important technique. Once you have a solution, you might have the solution only up to some accuracy, and you can improve the accuracy of this solution iteratively. And here is a procedure to obtain the iterative solution. Okay, so Ax equal to B is the equation for which we are trying to find the iterative improvement, right? So we know one solution X that we have obtained. We know the A matrix. So if you calculate AX and subtract from the right hand side, you have what is known as the residual. That is why it's called R. B minus A, some approximate solution X hat. Okay. Now you solve the equation AE equal to R. Now replace the X hat by X hat plus E. Okay. So we have the upper triangular matrix in the previous slide. So we have this upper triangular matrix for which we know the solution, the approximate solution, we can take it to be this, and then we see that R is this value, and you can solve A equal to R because you have the R values, you have A in upper triangular form, so solving for E is rather straightforward. It's just the back substitution, and you can add now this correction E to the X, and then you get the solution. So this in turn leads to the improved solution. So you can see that the solution is 411 and 10 power minus 2 and 10 power minus 3. But I started with minus 400.1 and 0.01, and you can see that I am reaching there, right? The second one is 7.8788 into 10 power minus 2, and I have got 7.8777 into 10 power minus 2. So in one step, by starting with a solution by close. So I can actually take the solution that I have obtained here, and I can try to find out to what error. I mean, I can calculate the error, and I can look at the E values, and if it is considerable, I can improve my solution or I can leave it. So it is possible to improve the solution, and it's also possible once you have gotten it in upper triangular form, just by using this iterative improvement, by taking some approximate solution, you can iterate, and quite fast you will converge to the actual solution. Okay. So this is another important technique. Unfortunately, we don't have the time to sit down and go through one by one, but I recommend that you try to do this algebra by yourself and confirm that the numbers I have given are correct. I'm notorious to give wrong numbers, so I'm not sure about my algebra, but you can confirm that I have done it right. Okay, so one last technique that you should know if you are solving system of linear equations is the Gauss-Seidel iteration. Okay, so it's an iterative procedure. Okay, in computer science we like iterations a lot, and yeah, so it is said that to iterate is human and to recurse is divine. Okay, so most of the algorithms are based on iterations and recursion. So it's really liked because computer can do such monotonic things quite efficiently and quite fast, and they have their own advantages. Okay, so iterative methods in terms of storage, for example, in terms of making the computations parallel, for example. So they have lots of computational advantages, which is the reason why we try to use them. And so elimination techniques are not that widely used on computers. They are very good for hand computations, but most of the times we end up using iterative methods. As you saw, I mean, like in the previous example, iterative improvement is something that is very nice. You can take approximate solution, and in one step you are converging to the actual solution. Okay. So in Gauss-Seidel iterations, we solve a set of equations iteratively. Okay. And this is an algorithm that works obviously better on a computer, and the Gauss-Seidel calculation is as follows. Okay. First we take the equations. Okay. And I'm giving the algorithm in a form in which it is easier to implement by hand, not using a computer. Okay. So this set of equations, in which now I will keep in the first equation A0 on the left hand side, and I will write its dependence on A1 and A2 to the right side. Second one, A1 on the left hand side, A0 and A2 on the right hand side, and the third one, A2 on the left hand side and A0 A1 on the right hand side. So you have the equations. So you can start with an initial guess for A1 and A2, right? You can put them here, and then that will give you an A0. You can use that A0 and your initial guess of A2 here, that will give you an A1. you can use that A0 and the A1 that you have calculated to calculate A2, and you can keep doing this, right? So if you keep doing it and keep using the updated values, that is the Gauss-Seidel. Okay. For example, if the initial guess is all 0, then what happens? So this is 0, this is 0, so 7798 by 6 will be the first solution that you will get, that is 1299.7. Similarly, this will become 0, this will become 0, so 8675450 by 3416468. So that is like a factor of about 3. So that is why you get, so A0 I have already gotten as 7798 by 6. So I am going to substitute that value, and this is of the order of 3 minus some number. Okay, so A0 I know is about 1000. So this is of the order of 1. So subtract this and then you will get the solution. So that is why you are getting 1.0. Okay. So now I can use this 12997 and 1.08 on this, and then subtract from this quantity, I'll get A2. So, so we keep doing this. So first you get this, and using this new guess value, you can do one more iteration, you will get this number. And so you can doing this. And when do we stop this iteration? We stop this iteration if we see that the solution is not changing much. Okay. So how do we check if the solution is not changing much? So at every step, you compare the current vector that you have got A0, A1, A2 with the previous vector you got. There are many different ways. You can look at the mod of different components, and you can find out largest mod, and you can say unless this becomes smaller than some number, I am not going to stop iteration. Or you can take the distance between the two vectors. So that is by taking component wise difference, squaring them, adding them all up, and taking a square root, and you can say unless this number becomes smaller than some value, I am going to keep doing it, and so on and so forth. So there are many different errors that you can define, whichever is something that you like. Or for example, you can take the difference between the components, you can take the mod, you can add all of them up, and that is another measure of error. Okay, so these errors have different names. L1, L2, L0, L infinity norms and things like that. So you can calculate whichever error you like, and you can predetermine that unless the error becomes less than this value, I am going to be doing the iteration. Okay. So in this case, about after 482 iterations, so obviously I didn't do it by hand. These are the first few iteration values. Again, using Octave will be very, very useful. So I strongly recommend that you go take a look at Octave. Making this iteration is so trivial. I mean, you just make the A vector, A matrix, and then generate initial vector, and then just keep saying Ax equal to, Ax equal to, and then you can keep improving the solution. Okay. So finally we get a solution, and this is a solution which is accurate to 10 power minus 6. Okay. So if I reduce my accuracy, I'll get it in a much lesser number of iterations. The large number of iterations obviously indicates that it is better suited for computers, and in the Gauss-Seidel algorithm also, will I always converge to the solution to that question? Here is the answer. The convergence to the solution is guaranteed only if the matrix is diagonally dominant or symmetric and positive definite. Okay. Diagonally dominant means if you look at the diagonal term, that should be larger than the other terms. Okay. So if they are negative and things like that, take the mod, but the other terms compared to them, this should be the large number. Okay. Symmetric, obviously you know what it means. So with respect to the diagonal, the off diagonal terms are the same. 1, 2, 2, 1 is the same, 1, 3, 3, 1 is the same, and so on and so forth. Positive definite means all its eigenvalues are positive, and so on. Okay. So to assure convergence, you should either have the matrix to be diagonally dominant or symmetric and positive definite. And the good news is most of the physical problems that we try to solve, these conditions are most of the times obeyed. So you can be sure of getting a solution and convergence to the solution. Okay, so I'm going to talk about the last topic. This again goes back to a question that I asked in the fitting problem. And that is that if suppose I have a specific functional form, how do I fit to that particular functional form? Okay, so we will use the same example. So we will take the same data, and what is data and what is the polynomial that we are trying to fit. We said that this is in boron nitride the thermal expansion coefficient as a function of temperature, and we said that it obeys the expression A0 plus A1T plus A2 T squared. That means for every temperature value there is an alpha value. Okay, so temperature is 77, there is an alpha. Temperature is 1205, there is an alpha. So there is a way to put that information, right? This is 1 times temperature squared. If you make a matrix, multiply by A0, A1, A2, that should be equal to the alpha value that you experimentally measure. So we have the alpha values, we have the temperature values. So we can make what is known as the design matrix. Okay. So that design matrix is what is shown here symbolically. Okay. So I have 1, I have 77, 200, 535, etc. up to 1205. I have the T squared value, it's basically square of this. And if I multiply that with A0, A1, A2, then I'll get this right hand side value. So this multiplied by this will be equal to 0, this multiplied by this will be equal to 0, and so on. So I have some n data points, then I can make n equations, but see the unknowns are only 3. Okay. So, and if you look at a textbook like Scientific Computing using MATLAB and Octave by Quattroni and Saleri, they will show you that solving this equation and getting A0, A1, A2 is basically equivalent to doing nonlinear least square fitting. Okay. So why that is equivalent to solving that is something that is described in that book. So I will not go into the details, but what we have to see in this is that so this could be any functional form, right? For example, if it was not A0 plus AT plus A2T squared, instead, for example, if it was A0 plus A1T plus A2T cube, then all I need to do is to put the cube of the temperatures in the third column, right? So then if I solve, then I'll get the corresponding. So it doesn't have to be, unlike the linear least square curve fitting where we took it to be the given particular form and then try to minimize. Here you don't have to worry. For example, it could be A0 by T plus T squared. Okay, so in which case all this 1 will be replaced by 1 by T, and that will be my design matrix. Okay, so design matrix is a neat idea. If you do that, then you can, if you solve that and get A0, A1, A2, then you have the solution for the given problem. Okay, so and what we need is that design matrix is not a square matrix. Okay, so we can use the Gaussian elimination method. So we can make several rows identically 0 and the rest as upper triangular. Okay, and that is, so you make all this 0 and you make these 3 upper triangular, and those 3 multiplying this equal to these 3 is the solution that we will be looking for. And once you get the solution, you can even do an iterative improvement on those set of equations. So that is possible. Okay. So this is what I said. So this kind of design matrix is useful because, for example, sometimes specific heat is known to have a specific temperature difference, AT plus BT cube. Okay, so A and B are the unknowns. So you make a design matrix with T and T cube, and you have the right hand side vector. So you can use Gaussian elimination to get, or stress strain curve if you are fitting y equal to mx. There is no c. Okay, so you have all the x on one side and all the y on one side, and m is the unknown. So you can try to get the m value using such a design matrix approach. Okay, so you have now a set of simultaneous linear equations. So we are revisiting the eigenvector problem. If we solve it, then we are done for solving simultaneous linear equations. So because we haven't done any hand computation today till now, and I just showed you, probably this is a good place to start. So the eigenvector equation, okay, so this is the eigenvector equation. So I have the 1 by 144 and then multiplying this matrix. So this is my matrix, and UVW, I need to choose the eigenvector in such a way that this is equal to 0. Okay. Why is this 0? Because we have chosen an eigenvalue of 1, and when you choose an eigenvalue of 1, okay, so it is 174 minus lambda, 174 minus lambda, 102 minus lambda. Lambda is 1. So it becomes 173, 173, 101, 30 minus 6, 30 minus 6, minus 6, minus 6, multiplying UVW equal to 0, right? So that is basically what the value that you found, right? Okay, so we have the equation now. This is the equation where we started talking about simultaneous linear equation. So you have an equation, okay, you can solve and you can show that the normalized eigenvector. So you will solve and you will get a vector and then take the mod of that vector, divide each component by the mod of that vector, then you will get the eigenvector. Okay, so the procedure, the calculation that I want you to do is to show that the normalized eigenvector for this problem is 1 by square root 2 minus 1 by square root 2 0. Okay, so it's basically on the xy plane and it's a line that makes 45 degrees and it is having x positive and y negative, so it is in the fourth quadrant. Okay, so it's a diagonal line on the fourth quadrant in the xy plane. That is basically the eigenvector for this problem. Okay, so in terms of crystal structure, please remember this is with respect to FCC. So the XCC A1, A2 plane and in one direction you have it. So it's important from that point of view. When we were discussing how much is the change in dimensions and along which direction and so on. We said that there is a direction which doesn't undergo any change in dimensions. So that is why the eigenvalue was 1. So this is that direction which doesn't undergo any change in dimensions. So that is what basically we are identifying by solving this problem. So what I would like you to do is to do this algebra. Okay, we will take a few minutes. I want you to solve this equation. You can use whichever method you want. You can reduce it to upper triangular form, use back substitution, or you can try to do Gauss-Seidel iterations, or you can you can try to find a solution using Gaussian elimination and improve the solution using some iteration. Okay, because iterative improvement is possible because you know the solution is 1 by root 2 minus 1 by root 2 0. So you take approximately the solution to be, for example, 1 by 2 minus 1 by 2 0, and then use the iterative improvement algorithm and try to see if you get to this solution, right? Root 2 is 1.414, so 0.707 is where the solution is. So start it somewhere around 0.5, for example, and then do you go to this solution. That is another way of doing it, and that is why I have indicated where the solution is. So whichever method that you want, please use it, and after a few minutes, I'll give you for 5 minutes, about 10:45 or so, then you can write to me in chat, or if you want, you can also raise your hand so we can have the audio and video. You can tell me which method you used and whether you got this as the normalized eigenvector or not. And I hope making progress. You can tell what is the method that you used and whether you got the solution or not. And as you can see, this is what I mentioned earlier. The matrix that you generate is very nice and it is diagonally dominant. You can see. In addition, it is also symmetric. I don't know about positive definite. Well, this should be positive definite because we have identified the eigenvalues and those were 0.71 and 1.4 or something like that. So you can see that most of the matrices that you make, you end up getting in real physical problems actually have this nice structure, because of which convergence is always guaranteed. In other words, what it means is that if you have formulated the physical problem correctly, you will be able to get a solution, right? I mean, that is obvious. So if your formulation is correct, most of the times you end up with very nicely behaved matrices, and hence the solution is guaranteed. Okay, so that is, unlike mathematicians, we don't have to be worried about lots of other mathematical aspects. If you get your physics history right, then math falls in place. Okay. So, please let me know if you are able to confirm that this is the eigenvector for the eigenvalue of 1. I think you can also make the algebra a little simpler by knocking off this 1 by 144. That is common to all equations. So taking it off means that you are multiplying all equations by 144. So that should not change anything. So you might be able to just take only this part of the matrix and do the computation. I think you will get the same answer. By the way, you can also write down the equations and then start eliminating variable by variable. Okay, so that is another possibility. Should also get you to the same. Okay, somebody using Gauss Seidel got the value 0, 0, 0. Okay, so Shobhan tells me that if you are using the starting point as 0, then you will get 0, 0, 0. So this tells you that even though we say that take a guess value, the guess value should still be consistent with the solution that you are trying to get. So if you put 0 everything, all the values multiplied by 0, so it will be trivially satisfied. Yes, Gauss Seidel will give you 0, 0, 0 if your initial value is 0. Okay, can you try with initial value something else and tell me where that takes you? For example, 1, 1, 1, start with 1, 1, 1 and see what happens. In other words, 0, 0, 0 is a solution, but it's a very trivial solution. So we are looking for a non-trivial solution, and that you should be able to get. Yeah, anybody else attempted? Okay. Gauss Seidel might also take large number of iterations. So probably better off trying some iterative improvement on a solution which is close, or by doing an elimination. As you can see, what I call and U and what I call as V, even if I interchange them, nothing is changing. Okay. So that is why one of the variables is, there are basically only two independent numbers that you are getting. Okay. Any progress? Or if you are using Gauss Seidel with 1, 1, 1, for example, what are the second or third iteration values? We can then move to the next problem if it is proceeding in the right direction. I see. This is if you use 1, 1. Okay. Elimination is not something that you tried. Okay. So, Shobhan tells me that if you take 1, 1, 1, the first iteration ends up with the 0.69. 0.069, 0.037. Okay. So if you're getting values like that, then you are proceeding in the right direction, and after a large number of iterations you are going to. So the actual solution is 0.707 minus 0.707 and 0. Okay. So probably elimination method will give this to you the quickest, and you can try. Okay. So I'm going to stop here at this point. We have spent about an hour, so the next 1 hour we will try to do the other problems that we have in mind. You can check this later when you get some time. And the next topic that we want to, optimization. Okay. So we are going to look at free energy minimization. So that is the most important optimization problem that you will come across in material science and engineering. And we will talk about search methods which can be used for doing the free energy minimization. I'll show you that free energy minimization basically reduces to finding zeros of a polynomial, and because we know how to find zeros of a polynomial, we know how to solve this problem. Of course, without making it finding zeros of a polynomial problem, you can use search methods to find the optimal solution. Okay, so we'll discuss that. Then we'll discuss what is known as linear programming, because that is one of the most important optimization problems that one comes across in engineering in general. Okay, but we will take an example which is related to material science and engineering and see what happens. So optimization is crucial. Most of our problems, engineering problems, are basically optimization problems. Know that you can do something and some property will improve, but at the same time cost will increase, or the time for production will increase, or some other property will degrade, and so on and so forth. So every time when we are choosing a material, choosing a process, choosing a component, we are making an optimization decision. Okay. So the most important optimization problem that one comes across is basically free energy minimization. Okay. So in systems in which temperature is a constant, it is easier to do a free energy minimization rather than doing an entropy maximization. But if temperatures are changing, non-isothermal processes, you have to do entropy maximization. But solid phase transformations, for example, they take place at constant temperature and constant pressure. So you can write the free energy, the relevant free energy, and minimize. Okay. So what we are going to consider today is a binary alloy, and it consists of A and B type of atoms. That's why it's a binary alloy. Okay. And XA and XB are the number fraction of A and B atoms. That is, XA is the total number of A atoms divided by total number of A atoms, total number of B atoms, and XB is total number of B atoms divided by total number of A atoms and total number of B atoms. So obviously XA and XB are related, so one of them can be written as 1 minus the other. We are going to assume that the interaction energies between AA, BB and AB atoms are given by EAA, EBB and EAB. Okay. And in a crystal structure with the Z nearest neighbors, and assuming that the system obeys a regular solution model for its free energy, the free energy change associated with mixing the A and B atoms on this lattice is given by omega XA XB plus KBT XA ln XA plus XB ln XB, where KB is the Boltzmann constant, T is the absolute temperature, and the constant omega, which is known as the regular solution parameter, it depends on Z and bond energies EAA, EBB and EAB. Okay. Now, the system, what will happen in the system will depend on what happens to this free energy. Okay. So if this energy, so you can write this in terms of one variable, because we know that XB is 1 minus XA. Let us call that one variable as X, then it is symmetric. So I can also write XA is 1 minus XB, and that XA I can call as X, and then you will get the basically the same expression. Okay, so there is a small thing you need to notice here. Okay, so the delta G mix is written as omega 1 minus X plus KBT 1 minus ln of 1 minus X. This bracket is missing in the expression I have written, plus X ln of X. Okay. So this is 1 minus X ln 1 minus X plus X ln X. Okay. So everywhere that parenthesis here is missing. So this is our delta G mix, and you can normalize this by dividing by KBT. So omega by KBT into 1 minus X into X plus 1 minus X ln 1 minus X plus X ln X. So this quantity then is the non-dimensionalized free energy of mix. You can find out what is the X that minimizes this quantity, and that X value will be basically the composition that the system would choose. Especially if omega is positive, then the system undergoes phase separation. So you can find composition of the two phases. If you know X, you know the other composition will be 1 minus x. So it will become a mechanical mixture of composition x and 1 minus x, and what x value at any given temperature for a given omega parameter is basically decided by the minimization of this quantity. So it's basically minimizing a given polynomial, and it is a polynomial with one variable, right? So we know the minimization, how it works. Basically you need to take the derivative of this polynomial with respect to x and equate it to 0 and you solve it. Okay, so when you have a polynomial equated to 0, then that is the problem of finding the zeros on the polynomial, which we have already discussed in greater detail when we are looking at the eigenvalue problem, because that was also another problem in which we were trying to find the zeros of a given polynomial. Okay, so obviously, so it reduces to something that we already know. So like I mentioned, omega is positive, then at lower temperatures the system undergoes phase separation, so it becomes a mechanical mixture of A rich and B rich phases. The composition of these A rich and B rich phases at various temperatures, if you calculate and plot, then we obtain what is known as the phase diagram. Okay, so the phase diagram computation is done. Okay, so the composition of the two phases, let us call this alpha and beta. Let A rich phase be alpha and B rich phase be beta, and it's determined by minimizing the normalized free energy of mixing. Okay, and so the problem to do is, so let's do the computation. Okay, so the normalized one is delta G mix by kBT is equal to omega 1 minus x into x by kBT plus 1 minus x logarithm of 1 minus x plus x logarithm of x. Okay, so what we want to do is d of delta G mix by kBT divided by dx equal to 0, because that is what is going to minimize this quantity, delta G by kBT. So if we do that, then what does that mean? So you have x, so that will give you 1 minus x, and when you differentiate, plus omega by kBT times minus x. So you get omega by kBT. So when you differentiate this, you get 1 minus x, and when you differentiate this, you get minus x. Okay, so that becomes 1 minus 2x basically. Okay, and when you differentiate this, you get 1 minus x, and that will give you 1 by 1 minus x, right, and with the minus sign. Okay, and then when you differentiate this, it will give you minus ln of 1 minus x. Similarly, that will give you x 1 by x plus logarithm of x, and this is basically 1 and minus 1, so they will go away. So that is equal to 0 is what we are trying to do. So you will end up with omega by kBT into 1 minus 2x plus, then you are only left with logarithm of this and this, logarithm of x by 1 minus x equal to 0. Okay, so you can use any of the methods that we have discussed earlier. So this is basically a polynomial, and so this is basically a polynomial, and we are trying to find the zeros of this polynomial, and we can use any of the methods that we discussed earlier to find the zeros of this polynomial and hence get the solution. Okay, so this is a factorization problem, and it can be solved using finding zeros of a polynomial algorithm. Okay, now we let's also look at some other methods. So there are search methods, so we want to discuss search methods. One of the things that the search methods would want, many of them would prefer to have, is unimodality of a function in a given interval. So what is unimodal? A function is said to be unimodal in a given interval if it encloses a single extremum point. Okay, so in this case, if it encloses one single minimum point in the given interval, then that would be unimodal. Okay, if it is unimodal, then lots of search algorithms are available, and they can identify the minimum without actually using this derivatives. So there are many such methods like interval halving method, Fibonacci method, and golden section method. There is a nice textbook by S.S. Rao called Engineering Optimization Theory and Practice, which discusses this and much more. So let us use the interval halving method. Okay, so we are going to do interval halving method to find the x value that minimizes the free energy of mixing, which is normalized free energy of mixing. Okay, so again let us consider this. Let us assume that this omega by kBt is 2.5. Okay, and when this omega by kBt is 2.5, this function, by plotting for example, I know that it is unimodal between 0.1 and 0.2. Okay. Now, the interval halving method that we are going to use is very similar to bisection method. Okay. In that it deletes 1/2 of the interval in every iteration to identify the point. Okay. So what do we have now? We have 2.5 into 1 minus x into x plus 1 minus x log 1 minus x plus x log x. Okay. So that is the function. Unlike the other method, we don't have to take the differentiation with respect to x and equate it to 0. Instead, we know that this function is unimodal between 0.1 and 0.2. So we are going to use interval halving method to find the point at which this value becomes an extremum, specifically in this case a minimum. So how do we do? So we divide this uncertainty, that is AB is the interval. So 0.1 to 0.2, we divide it into 4 equal parts. Okay. So we evaluate this function. Okay. So the midpoint is x0 and the quarter intervals, right? So this is a plus b by 2 is x0, but between a and a plus b by 2 halfway through, that is x1, and between a plus b by 2 and b halfway through, that is x2. Okay, so those are the quarter points, 1/4 and 3/4, those points are x1 and x2. So we evaluate the function at the 3 interior points, x1, x0 and x2. Okay, so you evaluate at the first quarter point, half point and the 3/4 point and call them as f1, f0, f2. If f2 is greater than f0 is greater than f1, okay, so f1, which is the first quarter point, happens to be the smallest, then midpoint is higher than that, then the third point is still higher than that, then we know that the function is having, and when we know that the function is unimodal, so it has only one minima. So we know that the interval where the minimum is going to be. So to identify that, label x1 and x0 as the new x0 and b. Okay. So what happened? So halfway through, a plus b by 2 and b is where the minimum is going to be. And so that is the interval. So we discard the interval between 0 and a plus the a and a plus b by 2. We discard that because we found that the function is actually trying to become smaller towards that way. If on the other hand, if f2, that is at the x2 is less than f0 is less than f1, we label x2 and x0 as the new x0 and a respectively and go to step 4. Okay, so and if it so happens that f1 is greater than f0 and f2 is also greater than f0, so then the minimum is somewhere in between the first quarter and third quarter. So we identify them as a and b. So the end 2 quarters we discard. So half of the interval is discarded. Okay. So now you keep doing this, and if the new interval b minus a satisfies the convergence criterion is what we look at. So once the b and a that we have identified, that interval becomes smaller than a particular interval, we stop and we have identified the solution. Okay. So like I said, this polynomial with 2.5 for omega by kBt has a minima in between 0.1 and 0.2. So we will first start with 0.1 and 0.15, which is between 0.1 and 0.2, and then 0.125 and 0.175 are the quarter points. Okay, so at those points evaluate and we find out what the values are, F1, F2, F3. Okay, so you take the first three values, then you see how they are, then depending on that you decide which interval it is going to be there. So and x0, x1, x2, then you calculate f1, f2, f3, and you keep doing that, and you can see that we are keeping from 0.15 to 0.1625. Initially we started with 0.15 and 0.175. Sorry, 0.125 and 0.175, and then the interval became 0.1375 to 1625. Then the interval became between 0.14375 and 15625, and so on and so forth. Okay, so if you keep on going, you will get the solution as 0.14374. Okay, so this is the interval hopping method. This method does not need any derivative, so you can just take the functional form and try to identify where the minima is. So geometrically, basically it is looking at how the function values are changed. Because it is unimodal, it has only one minima, so then it is easier to identify that minima. Okay, so let me move to the next type of problem, optimization problem, which is known as linear programming. In linear programming problems, the function which is to be optimized as well as the constraints that are posed on them, both are linear. That is why it's called a linear programming. The most widely used method to solve the linear programming problem is something known as the simplex method. So where do we use the simplex method? So let us find out. So there is a paper by OG et al. Okay, so the reference is given in my lecture notes. In that they show that for an sand casting experiment, for example, they are trying to optimize the parameters, where delta R, delta M, delta P are the deviation and process parameters. Delta R is basically the deviation in runner size, delta M is the mold temperature, and delta P is the pouring temperature. Okay, so these are the deviations, so they have some process parameters. So they are trying to find out the deviations that you can have in these process parameters, which will minimize the solidification time. Delta S is basically the solidification time. Okay, so and by doing lots of experiments, those are the details that is given in the paper. They have found out that the minimization is basically this quantity 0.005 delta R plus 0.002 delta M minus 0.013 delta P, that is equal to delta S. Okay, so that delta S is what you are trying to minimize. So you are trying to minimize this quantity, you are trying to make this quantity as small as possible, this deviation as zero as possible, but there are constraints. Okay, so the constraints are given by these four expressions. And you can see that they are all, the quantity that you are trying to optimize is linear, right? Previous case we had some x log x and 1 minus x log 1 minus x and things like that, highly non-linear functions. We are not having anything like that, it's just a linear function, and the constraints are also linear. Okay, so so we are basically trying to find out what is the deviations that is allowed, which minimizes this deviation in the solidification time. Okay, so you have some solidification time in mind, and your delta S cannot be more or less than a particular deviation. If you can pose this problem in this manner, then you can solve it using the simplex method. Okay, so how do we solve that? First, we introduced what are known as the slack variables. Okay. What are slack variables? So there are these inequalities in these equations, and we make them equality constraints by adding some slack variables. Okay, so this is less than or equal to this, so add some slack variable and make it equal to 5. Okay, which is what is being done here. So I have the four constraints. I have introduced four slack variables x1, x2, x3, x4. And by introducing them, I have replaced the inequality constraints by the equality constraints. Okay, So that is the first job. And then of course this is the first equation itself, which is written as the last equation in this form. Okay. When you write the equations in this form, you are said to be having the linear programming problem in the standard form. Okay. The simplex method, so this is the first step, and we are ready to start the simplex method. What do we do in the method? We consider the slack variables that we have introduced, x1, x2, x3, x4, and the value that you are trying to optimize delta s as the basic variable, right? So I have these 4 and this minus delta s. So I consider these to be the basic variables. What that means is that the rest of them I am going to assume that they are 0. Okay. If I assume those to be 0, right, then I get the solution x1 is 5, x2 is 5, x3 is 5, x4 is 5, and delta s equal to minus delta s is equal to 0. So we start with this first solution, and with this solution we are going to try to find a solution which actually gives us the optimized value. So that is the method. Okay. So when we do that, we find that the cost coefficient, right? So in this equation, this is positive. These are known as cost coefficients in the optimization, what you are trying to optimize in that equation. This is positive, this is negative. So the quantity which has the negative cost coefficient, okay, so we find that a non-basic variable, the cost coefficient associated with a non-basic variable is negative. So this solution is not optimal. Okay, if all the cost coefficients for all the non-basic variables become positive, basically then we have achieved the optimal solution. If there is more than one, of course this method will tell you which one to choose first and which one to choose later, and so on and so forth. But in this case, there is only one cost coefficient which is negative, which means that has to be brought into the basic variables. So we have to replace x1, x2, x3, x4, one of them by delta p. Now the question comes as to which one of these I am going to replace, right? Any one of them can be replaced, and that becomes a non-basic variable, and delta p becomes the basic variable. We can do that. Then that is the algorithm. So simplex algorithm tells you how to do that, and here is the description. Okay, so we have a current basic feasible solution in which we have x1, x2, x3, x4 as 5 and minus delta s as 0. But there is one non-basic variable with a negative coefficient. So we want to bring that into the basis. Okay, if there are more than one negative coefficient, the one with the largest negative value will be brought into basis. Okay, so in this case minus 0.013 is there, but suppose if this is negative and this is negative, then also this will be chosen because that has the largest. But if it is minus 0.013 and this is minus 0.53, then that will be brought into the basic variable, and then the algorithm will proceed. So okay, so in this case we have only one, so we can bring delta p into the basis. While bringing delta p into the basis, okay, so we need to choose a pivot element. I'll show you how it is done, the pivoting, so that the ratio of right hand vector component to the coefficient of delta p is the smallest. Okay, so we need to choose the pivoting element so that the coefficient of the right hand side to the delta p is the smallest. So for that to be smallest, then we need to choose whichever delta p has the largest coefficient. If we choose that, then that will be the smallest, because 5 because right hand side is the same. If the right hand sides are different, then you need to take the ratio and find out which coefficient actually gives you the smallest right hand side divided by the coefficient value. But because they are all the same number, then we know that if I choose the largest one, then 5 divided by 0.166 will be the smallest as compared to all these numbers, because 5 divided by 0.01 will be larger, 5 divided by 0.001 will be still larger, and so on and so on. Okay, so that is the next step. Pivot element is chosen such that the ratio of the right hand side vector component to the coefficient of delta p is the smallest. In our case, all the right hand side vector components are 5. So the smallest is the one with the largest delta P coefficient, and that is what is chosen for pivoting. Okay, so that is the first equation in which the coefficient of delta P is 0.166. That is chosen as the pivot. What do we do with the, using that as the pivot? We make the coefficient of delta P to be unity in the first equation and 0 in all the others. Okay, so these operations are understood far more easily by putting it in the table format. Okay, so delta R, delta M, delta P, these are the coefficients. These are the slack variables that I introduced, x1, x2, x3, x4, and the minus delta S has the coefficient of 1, and the BI values is 5550. Now of these cost coefficients, only this is negative. If there is more than one negative, I will find whichever is the largest negative number, and then I will choose that, or mod largest with a negative sign, I will choose that. In this case there is only 0.013, so I choose it, and then I decide to replace one of them with one. It could be this one, this one, this one, or this one, but I want to choose the one which has the largest value for this right hand side divided by the coefficient. That number should be the largest. Because the right hand side is the same in this case, then whichever is the largest, if I choose, then that will be the smallest number that I will get. Okay, so 5 by 1.666 will then be the smallest, because anything else 5 dividing these numbers will give you larger values. So then I use this as the pivot point. Now what do I do with the pivot? Then I want one here. See, the basic feasible solution was obtained because this had 1 here and 0 everywhere else. X2 had 1 here and 0 everywhere else. X3 had 1 here and 0 everywhere else. And X4 had 1 here, 0 everywhere else. What does that mean? That in only one of the equations it showed up, in all the other equations it disappeared. Now we want to replace one of these non-basic variables, one of these basic variables by this non-basic variable delta P. We are replacing it because delta P has this negative cost coefficient. So while doing that, that means that this should become 1, everywhere else it should become 0. And while doing that, one of these variables will become non-zero everywhere, and then that will then become the non-basic variable, and the rest will remain as the basic. What is the step? So you want to make this 1. How do we do? You can do that by simply dividing by 0.16. If you divide everything by 0.166, then you will make this as 1, right? So you have divided the 5 by 0.166, and that is why you are getting 30.120. Okay, so you are dividing 1 by 0.166, and that is why you are getting from 6.0, and so on. Okay. So after you have divided, then you have these values. Okay, so but we not only want to get this 1, but we also make this to be 0. Okay. How do we make them to be 0? For example, if you did all these numbers by 0.0 to 1 and subtract these values from this, because this is 1 now, because it's divided by 0.0 to 1. So 1 minus 1 will become 0. So this quantity will become 0. But in the process, the other numbers will change. Right? Here also, if I divide all the numbers by 0.057 and subtract, then I will get this also to be, in this line also, this coefficient to be, and so on and so forth. Okay, and because I'm going to, so I'm going to divide each one of these rows by these coefficients in delta P, and then I'm going to take, so this is exactly like the augmented matrix operation. So I'm going to replace these lines by the linear combination of itself with the other lines. And in this case, all that I'm doing is I'm taking this first line minus that line itself with this coefficient made 1 by dividing by the corresponding coefficient. That is what I'm going to replace. Okay. Now, accidentally, this is not by design. When I did that, I put the slides, and in the slide, all the other terms are available, the B term is not available. And that is the exercise for you. I want you to do this operation. Okay, I hope the operation is clear. For example, in this, you divide by 0.021, you divide all the quantities by 0.021, and you subtract, for example, minus 0.28916 minus 0.031 by 0.021, and subtracting, that will become plus. So it is basically minus 0.28916 plus 0.031 by 0.021. That quantity is what will be put here. And similarly, 0.033 by 0.021 is some quantity. From 1.1807, subtract that quantity and put here. 0.021 divided by 0.021 is 1. 1 minus 1 will become 0. This is 0 divided 0.021 is 0. So 6.021 minus that 0 is basically 6.02. Okay. This is 1 by 0.021. From 0, if you subtract, it will become some minus quantity. And this is 5 by 0.21. So 30.120 minus 5 by 0.021 is the quantity that should go here. Can you do that calculation and tell me what that number is? So basically what I want you to do is to calculate the quantity 30.120 minus 5 divided by 0.021 is equal to what? So that is basically the quantity that will go for B here. Similarly for others, right? In the third column, for example, you will have 30.120 minus 5 divided by 0.057, right? And in the fourth one, you will have 30.120 minus 5 divided by minus 0.001. Okay, so this minus and minus is going to become plus 1 is equal to 1. And in the last one, okay, so you have 0. So you have and it doesn't matter by which number you divide. So you have 30.120 minus and 0 divided by minus 0.013 equal to 1. So this is what you are going to get. So can you calculate these numbers and tell me what they are? Okay, so this is trivial. This is 30.120 itself. So can you calculate these three numbers and tell me what they are? You can type it in the chat window. We will see what those numbers are. Of course, they are to be done for each one of these columns. So I'm going to show you, if you do the algebra, what those numbers are going to be. But the last column is missing. Okay. When I prepared the slides, I didn't realize that it was missing, but it's a good thing that gives you a chance to do a small computation and check for yourself that we are in the right direction. Yes. So I have got one answer. Minus 208 minus 57.5 and 5030.1. Okay. 5030.1 is correct because it is 5 divided by 0.001. So that is 5000. So it's basically 5000 plus 30.12. So it is 5030.12. The other values, minus 57.5, it is minus 57.6 or minus 57.599. That's what I have. Again, there could be numerical accuracy issues. And the first number is again minus 207.98. So that I think is approximated to 208, which is okay. Okay. So those are the correct numbers. So if you do the computation for all, so then you get this as the matrix. But along the way, you realize that all the cost coefficients in the last column have become positive, which means the method has identified an optimal solution. What is that optimal solution? The optimal solution is one which has delta P, because that is 1 and rest is 0. So that is part of the solution. And the x1 has become non-basic. Previously x1 was part of the solution, but that is what got replaced by delta P. And that whether x1 will replace or not was decided by looking at the ratio of right hand side divided by the coefficient of delta P. Whichever is the smallest, that is what we chose. Okay, because whichever is smallest then is the least constrained constraint. Okay, so that's why we are choosing that. So we decided to replace the rest of them. X2, X3, X4 are basically the part of basic feasible solution. And for that, what is the delta S value? That is also, see, if this is any one of them are still negative, then or while doing this, if one of them becomes negative, then for that again you will look at the coefficients. You will look at the right hand side coefficients. You will take the ratio, whichever is the smallest, you will choose that variable. Then you will replace, you will make that as the basic variable, and you will replace the corresponding one by the and make it non-basic variable, and so on. Okay, so now because the values are given using the right hand side values, for example, minus 207.98, right? So delta P itself has become 30, and minus 47.619 equal to minus 207. So x2 basically will become minus 207.98 by minus 47.619, and x3 will become minus 57.599 by minus 17.544, and x4 will become 5030.12 divided by 1000, and actual the delta S value will become 30.120 by 76.920. So that is what is given here. So the basic solution is by assuming delta R, delta M and x1 to be 0. So the solution is delta P is allowed to change by 30.120. The other variables, x2, x3, x4, which are the slack variables that we introduced. Those are the variables that were introduced to make the inequality to be an equality constraint. So these are the values by which they are allowed to change. So those expressions, that those inequalities are to be within this limit, and the optimum value for delta S. Okay, so what is the deviation that you can allow? That deviation cannot be greater than 0.5. Okay, so this is the solution. So so this is how you solve linear programming problems. There are many different types of linear programming problems. S.S. Rao gives several examples, and they are very common. Of course, if you go through OG's paper, you will find out that getting to these equations is basically also lots of experiments. You need to do plenty of experiments, find out the dependence of these variations on the properties that are of interest to you. Using them, then you have to pose the problem. Once you pose the problem, this very simple algorithm, which is basically a set of algebraic operations, and then that gives you the, okay. So there are two problems that I have given. Okay. One is to use bisection method to find 0 of the function, where omega is 2.5. We have already identified a solution for this particular case, but by using the direct method, interval halving method. Okay, and then to find the minima of the curve in the interval 0.1 to 0.2 using interval halving method. So this is what we discussed. Okay, this is what we discussed during the session itself. So when you use bisection method and replace this by 2.5, so 2.5 into 1 minus 2x plus ln x by 1 minus x equal to 0. So what are the zeros of this function when you assume the interval 0.1 and 0.2? Okay, so can you use bisection method to find the 0 and tell me how many iterations and you converge to what value. We will take a couple of minutes, so you can at least try to do one iteration. Take 0.1 and 0.2 as the bisection interval and tell me whether it lies between 0.1 and 0.15 or 0.15 and 0.2, for example. Okay, you can just do that computation. So the computation is very simple. So you will put 0.1, you will put 0.15, you will put 0.2, you will find out which two values, right? F of 0.1 into F of 0.15, what is its sign? F of 0.15 into F of 0.2, what is its sign? Okay, whichever sign is negative, then it is in that range that the solution will fall. So I want you to do that computation and tell me whether the solution falls in 0.1 to 0.15 interval or 0.15 to 0.2 interval. That brings us to the end of the optimization module. So please do that computation and tell me. You can post the answer in chat. Then we will move to the next part of the module, which is on solving ordinary differential equations. It requires 3 evaluations of this function, and the points of evaluation are 0.1, 0.15 and 0.2. Just by looking at the numbers, you will know whether f.1 into f.15 is negative or f.15 and 0.2 is negative. At least one of them has to be negative, because if it is not negative, then the solution is not bounded in this range. Okay, both cannot be positive and both cannot be negative. So only one of them will be negative, and I want to know which range gives you the negative value. 1.5. Okay. Okay, so you will find that we found the solution earlier, so it is below 1.5. So in the range 0.1 to 0.15, you should find f of 0.1 into f of 0.15 to be negative, f of 0.15 into f of 0.2 will be positive. Yes, right? So you find that is the range in which you have interval. Okay, so I have one answer. Very good. So we will go to the last part of this course. Okay, over the next 15 minutes or so, we will discuss one of the most important problems that you will come across, which is solving ordinary differential equations. Of course, most of the times we are also interested in solving partial differential equations, but solving partial differential equations using numerical methods will be a separate module by itself. It will take that amount of time for us to discuss the available methodologies, and some of them are very involved. So we will not talk about it, but ordinary differential equations is something that one comes across very often, and is also very useful to know how to solve. These methods are very trivial, so there is a reason why these methods work, how these algorithms are developed, or what is the reason why the algorithm is the way it is. I recommend that if you are interested, you take a look at Kreyszig's classic textbook, Advanced Engineering Mathematics. So it gives you the algorithm and it explains how it works and so on. But in this course, we will just take the simple approach of implementing the algorithm, and we are going to do by hand. So we will just take the algorithm, we will take the equation, and we will try to solve it numerically, wherever possible compare with the available analytical solution, and then move on. Okay. So in many problems, so when you pose it as a mathematical problem, you end up with an ordinary differential equation. Okay. So we need to obtain the solution for the ordinary differential equation under the given boundary condition. There are several numerical techniques which are used to obtain the solution for ordinary differential equations. So we will discuss two. One is known as improved Euler or Hume's method. The other one is classical Runge-Kutta method. Okay, Runge-Kutta method of fourth order is what we will discuss. Okay. So first problem that I would like to discuss where we will use Euler's method is the following. So you have a tank, it contains 100 liters of water and 20 kilograms of salt is dissolved in this 100 liters of water. Okay. Now 2 liters of brine, that is salt water, each containing 1 kilogram of dissolved salt run into the tank per minute, and the mixture is kept uniform by constant stirring. So you have an inlet which keeps giving 2 liters of brine per minute, and those brine that is coming in, each liter contains 1 kilogram of dissolved salt, and from the mixture we keep taking 2 liters out every minute. So the amount that is coming in and the amount that is going out is the same, but there is some salt concentration in the incoming liquid, there is some salt concentration that is in the outgoing liquid. So we want to know as a function of time, say after 10 minutes, what is the amount of salt in the solution, right? So every minute you get brine and that has a particular salt solution, and the original solution in the tank, the 100 liters, that has some concentration of salt by itself. So what is the, how do we the salt concentration as a function of time in this tank? So this problem can be formulated as an ordinary differential equation, and the principle we use is very simple. That is the law of conservation of mass, right? So the total amount of salt in the tank at any time t, let us say that is y. Okay. So what we are interested in is the rate of change of y, so dy by dt. Okay. So that is how does the rate of the amount of salt in the tank change with time? That is nothing but how much is coming in minus how much is going out. Okay, so inflow is 2 kilograms per minute. Okay, and the amount of water in the tank is always 100 liters. Okay, so because 2 liters enter and 2 liters leave, so outflow is 2 times, but the salt concentration in that is y at that particular time divided by 100 kg per minute. Okay, so now what does the mass conservation tell you? So dy by dt is equal to 2, that is the amount of salt that is coming in, minus 0.002y. Okay, and y0 is 0.2 because that is the initial concentration of salt in the tank, 20 kilograms per 100 liters. Okay, so that is basically the initial concentration, and dy by dt 2 minus 0.002y. So this is basically the inflow minus the outflow, and y is changing as a function of time, and the rate of change of y with time is basically decided by this. Okay, so that is the initial value. Now you can solve this analytically, and you can find out what is y at time t equal to 10. Okay, so what do we do? In the improved Euler's method, of course, when you have analytical solution available, you will not bother, but there are equations for which analytical solution might not be available. Then we want to numerically integrate. But in this case, even this equation we are going to numerically integrate so that you can understand how the method works. Okay. So if x0, y0 are the initial values and h is the step size, okay, that is time in our case, and n is the number of steps. Okay, suppose we want to get 10 minutes and we can take a time step of 2 minutes each, and in 5 steps we will reach 10 minutes. Okay, the approximation for y at any time n plus 1, y at any time t n plus 1 is basically given by this expression. What do we do? We take the time step, Tn plus 1 is Tn plus h, where h is the time step, and k1 is h times the function evaluated at x and yn, k2 is h times the function evaluated at xn plus 1 and yn plus k1, because we have evaluated k1 here, and yn plus 1 is nothing but yn plus half of k1 plus k2. Okay, so this is the simple algorithm that we use to calculate the solution at any time y given this function. Okay, so in our problem f of x comma y is 2 minus 0.002y. Time t equal to 0, let's take a step of 1. In the first step t is 0.1 because it is 0 plus 0.1. Okay, k1 is nothing but 0.1 times f at x and y. Okay, so x0, y0. X0 is not part of this function, only y0 is part of this function. So 2 minus 0.00 times y of 0. Y of 0 we know is 0.2. So it is 0.1 into 2 minus 0.002 into 0.2. So that is 0.19996. K2 is now 0.1 times f x comma y plus k, k1, right? So we know, so that is what the algorithm said. So yn plus k1, and so we take the value. So it's k2 is 0.1 into 2 minus 0.002 into, this is the k1. What is yn? So it should be yn plus k1, and yn is 0.2. So it should be 0.2 plus 0.19996, so 0.3996. So that value should be evaluated. That is K2. So if you take y at point, for example, is 0.2 plus 0.5 into K1 plus K2. Okay, so whatever 0.39 you put, whatever value you get, you add it, and that will get this. So you have the analytical solution. You can compare this solution with the analytical solution, and using current solution, you know now at time 0.1 what is the y. So using 0.1 and y at 0.1 this value, you can go and get it at 0.2 and so on and so forth. Okay, so by doing this, you will get the solution generated. Now the next method is the Runge-Kutta method. For the Runge-Kutta method, we will use an example which is from a quenching problem. What is the quenching problem? Suppose you have completed a heat treatment experiment and removed a sample from furnace at 2 p.m. in the afternoon. Okay, at 2 o'clock in the afternoon, you have removed your sample from the furnace. Now the temperature of the sample at 2 o'clock is about 1000 Kelvin, and the room temperature, let us say, is 303 Kelvin. Okay. Now what will be the temperature of the sample after 15 minutes, assuming that the cooling of the sample obeys Newton's law of cooling, and the value of the constant of proportionality is minus 0.005 in our per hour time units. Okay. So what does Newton's law of cooling say? It says rate of change of temperature is this constant that is given as minus 0.05 times current temperature minus the room temperature. I mean, this is the temperature in which the sample is, this is the temperature of the surrounding medium. So the difference is basically decides how much will be the rate of change of temperature. And we know that at time t equal to 0, the temperature is 1000. Okay. So what we are interested in knowing is what is the temperature at time 0.25, because we said after 15 minutes, and this is in per hour time unit. So 15 minutes is basically a quarter of an hour. So that is t.25 is what we are interested in knowing. The methodology that is used, Runge-Kutta method of fourth order, again you have x0, y0 initial value, h is the step size, and n is the number of steps, and the approximation, basically it is similar to Euler's method, as you can see, but it takes steps before it gets you to the final solution. How does it do? So you calculate at xn, yn, in this case temperature, so xn, tn, and xn plus half h and tn plus half k1, and then xn plus half h comma tn plus half k2. So that is k1, and then using k1 you get k2, using k2 you get k3, and then you get xn plus h and tn plus k3. So using k3 you get k4. Once you have obtained all the values k1, k2, k3, k4, so tn plus 1 is nothing but tn plus 1/6 of k1 plus 2k2 plus 2k3 plus k4. Okay, so this is the method that is used, and that brings me, so I have done the computation. So let us take our problem. T is 0, H is 0.25, T is 1000. So in one step I am trying to calculate the values, and if I get, if I do the computations, then I get something like, after 15 minutes the temperature would have reduced from 1000 to 994.855. Okay, so this is the solution I get. You can compare this with the another solution. Okay, so that brings us, unfortunately we didn't get too much of time today to do many of these computations, but this is time up. So I'm going to stop here. Please feel free to write to me in case you have any questions or clarifications, or you need more material. You can also look up on, there are more materials of this type that is available, and some of which also prepared by us, which is available. Okay, so if you have any questions or comments, I'll take. Otherwise, I'm going to end the session. Hey, any questions? Any doubts? Any clarifications? Okay, so if there are no questions, thank you very much.